So my name is Rita Dantas, and I'm a PhD student from the University of Porto. First of all, I'd like to present you the main topics of this presentation. I will start by introducing you the main motivation and goals of this work. Then I will explain materials and methods that we consider, the experimental work and results that we obtained, and finally, the analytical model that we consider to handle the frequency effects and the discussion about the achievements of this work. So during the last decades, the sustainability in engineering structures became a concern of our society. And when we think about sustainability, we think about structures with longer service lives. And because of that, it's important to analyze and assess the fatigue behavior of materials for higher number of cycles. And when we speak about higher numbers of cycles, we speak about here the region of very high cycle fatigue regime, as you can see here in figure 1, where we have lives higher than 10 millions of cycles. However, to analyze this regime, we need to test our specimens at very high frequencies, and usually for that we use ultrasonic fatigue testing system that I will speak during this presentation. And because of that, sometimes we have in certain materials a thing that we call the frequency effect. This frequency effect can be caused by different factors and aspects. Usually in literature, we can divide these into main groups of causes. One of them is the test typology. For example, when we have different testing systems, we need to have different geometries to be suitable for the testing system. And because of that, sometimes we have different risk volumes, which will affect our results. Besides that, for example, for the ultrasonic fatigue testing, we have heat generation, which can also affect our data. And besides that, we have the load type or level. For example, when we have ultrasonic fatigue machine, usually we perform our tests under displacement control, and usually in more conventional machines, we perform our tests under load control. Besides that, we also have some causes regarding material, and this work will be more about this. Usually when we speak about material causes, we speak about strain rate. Usually the materials that are more sensitive to frequency effect, they are also very sensitive to the variation of the strain rate. Besides that, we also have important rule of the ultimate strength and of course lattice structure that in fact affects the strain rate and ultimate strain. And finally, we have the mechanism of failure, because usually sometimes in very high cycle fatigue regime, we have a switch from the surface crack initiation to internal crack initiation. So the main goal of this work is to assess the frequency effect in different metals and try to correct it to have to be able to analyze the fatigue behavior of materials for real case scenarios. So basically, we studied 3 different materials. We studied a structural steel, a spring steel, and an aluminum alloy. Of course, that the structural steel and the spring steel are very similar. They have both a body center tetragonal crystal structure. They are tempered martensite. They show tempered martensite microstructure, and they also have a considerable high ultimate strength. On the other hand, the aluminum alloy has a face-centered cubic crystal structure and is more ductile, and it shows a lower ultimate strength. So basically, we tested this material in 3 different setups. We consider a conventional fatigue bending machine to test at 20 Hertz, and then a resonance fatigue machine to be able to test our specimens at 100 or 150 Hertz. It depends on the material properties of the material that we are testing. And of course, here in figure 5, you can see the setup of the ultrasonic fatigue machine that we consider to test our specimens at 20 kilohertz. It's important to mention that we decide to perform all of our tests under the same stress ratio of -1. And as I was saying before, usually when we have different testing systems, we need different geometries. And you can see here a summary of the geometries that we consider for our experimental tests. As you can see, for the structural steel and for the spring steel, we consider the same geometry for the bending machine tests and the resonance machine tests. However, for the ultrasonic machine, the geometry needs to be a bit different because of the work principle of the machine. And in case of the aluminum alloy, we only test specimens for the resonance machine and for the ultrasonic machine. As you can see here, we have some dashed lines for the bending machine because we were not able to test at lower frequencies. However, for the resonance machine, where we have 100 Hertz of frequency, we tested two different geometries, as you can see here, to analyze a bit the frequency, the size effect. However, this was not the main topic of our work. So basically, we tested our specimens, and I'm going now to show you our main results. Here you can see here the results that we obtained for the structural steel. We have a significant frequency effect. I think it's it's surprising, but in fact, all of this data is from the same material and from the same batch, however, tested at different frequencies. But we were sure that we had exactly the same conditions. We polished the specimens in the same way, and we controlled the manufacturing process. However, we have very different results. You can see here that the frequency effect increases with the number of cycles, and in fact is a non-linear behavior. So it will be more significant for a higher number of cycles. Besides that, we also observed the mechanism of initiation, and we observed that most of the cracks initiated from the surface, and we also have a frequency limit here around 10 millions of cycles. For the spring steel, the behavior is very similar. However, we observe a couple of internal crack initiations. However, we continue to observe a frequency effect that increases with the number of cycles, and this is non-linear, which is more difficult to handle. On the other hand, for the aluminum alloy, the behavior is different. You can see here that, in fact, the mean curve that we obtained for the 20 kilowatts only show a upper offset. So we have a linear and constant difference of the frequency behavior. In fact, we were kind of surprised to observe a frequency effect because this material has FCC structure, and usually for this kind of crystal structure, some authors report that the frequency effect is not visible or can be ignored. However, in our case, we notice a frequency effect, and we think that is because of the heat treatment of this alloy, since it induces the presence of precipitates that will change a bit the dislocation movements. So at this point, we thought that we needed to apply a model or an approach to handle the frequency effect, to obtain a mean curve, a probabilistic curve, something that we could use to analyze the fatigue behavior of a structure. And for that, we considered the four-dimensional Castillo-Cantelli model and combined it with the Tuasa-Kaisa approach. I'm not going to detail these approaches very much because they are a bit complex. You can see here the reference to check these models. They are very interesting models because, for example, for the Castillo-Cantelli model, they basically define a damage parameter based on four variables: the number of cycles, the stress ratio, the maximum stress, and of course, the most interesting part, frequency of testing. And you can see here a summary of the algorithm that we defined and introduced it in MATLAB. Basically, we have a first part where we apply the Castillo-Cantelli model, and this is basically two nonlinear optimization problems. The first part we obtain regression model, and then we can obtain the probabilistic parameters. And after that part, we also consider the information from the runouts. This is an iterative process, and at the end we can obtain a mean curve and the probabilistic curves that consider the data also from the runouts. You can see here the results that we obtain for the structural steel. Of course, that now we have a different stress amplitude. It's an effective stress amplitude instead of the nominal stress. And you can see that this new parameter can describe very well the data from all the frequencies that we tested. Besides that, we could use the runouts information, and we obtained this for the structural steel. For the spring steel, it also worked very well because we have our experimental data that can follow only a single mean curve. And finally, for the aluminum alloy, the results were quite good. However, for the aluminum alloy, in fact, maybe this is not the most suitable model because we have a simpler behavior to describe, and besides that, we don't have a fatigue limit as in the other steels. And this model predicts an horizontal asymptote as the number of cycles increase. However, we think that with this model, we were able to describe very well the frequency effect. So the conclusions. We tested 3 different materials with different crystal structures. We observed that for a BCT crystal structure, we have a frequency effect that increases with the number of cycles. And on the other hand, for the material with the FCC structure due to the precipitates, we also will have a frequency effect, however, is less visible and remains constant with the number of cycles. And we also conclude that the 4-dimensional Castillo-Cantelli model works very well to account with the frequency effect. And in fact, I think that it was the first time that this model was applied for this kind of ultrasonic frequencies. And in the future, we expect to analyze other materials with other crystal structures and also improve a bit the optimization problems that are not so simple to apply. That's all. Thank you for your attention.